In past videos, we talked a little bit about orbital diagrams, so this is going to be a little bit of a review, but I want to talk a little bit more about orbital diagrams to get us into a conversation on electron configurations and how they relate to the periodic table, because the periodic table is such a strong symbol of chemistry, and we can get so much information from the periodic table that it's important to be able to figure out kind of how we get and where we get the different pieces of information here. So let's think about sodium. We know that sodium's symbol is Na, which stands for natrium, which comes from the original term for sodium. And because of its atomic number, it has 11 protons. So that means in a neutral atom of sodium, I have 11 protons and 11 electrons. I need to have the same number of plus signs as minus signs. So if I'm thinking about the electrons on that sodium, again, thinking about where they most probably are going to be, they're going to want to be in the lowest energy configuration. So we've built these diagrams before and said, my energy here is along the y-axis. My nucleus would be down here at the bottom. And when I'm talking about the electrons filling in, they're going to fill in 2 per atomic orbital, because each of these orbitals, which is represented by a hyphen here, can hold up to 2 electrons. And one of them is going to be spin up and one is going to be spin down. So I have 2 electrons in my first atomic orbital here, my 1s orbital, which means if we're relating this to the Bohr model of the atom, that I have 2 electrons in the first shell. So remember, our Bohr model of the atom kind of looks like a bullseye, where each of these shells represents the energy of the electrons that are in there. So this would be quantum number, principal number n, which is equal to 1, 2, 3, etc. And the numbers get larger as we get away from the nucleus. So if I have 2 electrons in there, these 2 electrons and these 2 electrons are symbolically the same. I'm using just kind of 2 different ways to model them. Now I also have 2 in the 2s. So far I've accounted for 4 electrons on this sodium atom, so I still have 7 to go. I'm going to fill in my 2p with all of my arrows pointing up. The arrows again are representing electrons. The up arrow indicates that they are spin up. I'm going to put the spin up and spread them out as much as possible before I pair them up. Okay, and that's called Hund's rule, right? So we're going to spread out the electrons as much as possible before we pair them up. And that's an important feature kind of as we move forward and as we're predicting where electrons can be. They don't like to be all wadded up in the same way that if I was to release a certain amount of gas in a room, it's not going to stay clustered up on one side. It's going to dissipate. It's going to spread out. And electrons like to do the same thing. Okay, so how many have I used up so far? I've used 2, 4, 6, 8, 10. The first 2 there are in my first shell. That 1 here again is my, if I'm thinking in terms of quantum numbers, this is n, the principal quantum number. Which tells me the shell number if I'm thinking in terms of the Bohr model of the atom. In my second shell, I have both s and p orbitals. So the s and the p is my orbital type, and that's reflected by my m sub l, or my L value, sorry, which is my angular momentum quantum number. M sub L is our next one. Now the fact that there's 3 different orbitals in there, so there's 3 different orientations of my p orbitals, that fact is due to the magnetic quantum number, which is m sub L. And kind of depending on the level of chemistry you're learning, this is going to matter more or less, kind of depending on what that is. So n is the principal quantum number. L gives you the type of orbital it is, s and p. The magnetic quantum number gives you the orientation of it. So p orbitals can be along the x-axis, they can be along the y-axis, they can be along the z-axis. So those 3 different orientations I represent with 3 different orbital types. That's your m sub L. And then the last one is m sub s, which is the spin quantum number. And that just means, is it spin up or is it spin down? So in that way we represent kind of the up and the down arrows, and this has to do with which way the electron is spinning, which is a characteristic that kind of gets into some quantum physical way that matter interacts kind of features. So definitely more of the physics realm of things. Now, so far I have 8 electrons then in my second shell, which if I'm being consistent with my Bohr model here, I'd represent those 8 like this. And then I've accounted for 10 so far. I need 11, so I'm going to put 1 in my 3s. So that would be 1 in my third shell. Okay, so this is one way to do an orbital diagram. Again, this is review, and I'm kind of relating some of these new topics to it with the different quantum numbers. These 4 quantum numbers, the n, the l, the m sub l, and the m sub s, are very useful in terms of orienting and locating electrons on an atom. And again, as chemists, we really care about where the electrons are, especially the highest energy valence electrons, because those are involved in all the bonding, in all the gaining and losing, in all of the different interesting chemical type reactions. The ones that are lower, like the ones in my 1s here, are more shielded from any interaction with other atoms, right? If I have another atom that comes in and interacts with this atom, it's going to interact with the electrons in the outermost clouds or outermost energy levels or outermost shells or outermost orbitals. Kind of as you're visualizing all of that, then this is the way that they're going to be interacting. Now, another way you will sometimes see orbital diagrams is with either boxes, or I've seen bubbles as well. And the scale that we're looking at here is increasing energy along an x-axis, which is fine. We often will think about things as a number line. I personally prefer the orbital diagrams where we're going up the page towards higher energies, where we're kind of stacking our orbital types, because in my mind, this fits better with the Bohr model, which is the way that I often am thinking about the atom. So the energy along the x-axis works as well, and if we were filling this in for sodium, we'd say there's 2 in the 1s, 2 in the 2s, 2 in the 2p, 4, 6, and of course with Hund's rule I'd fill them in 1 box first at a time. I knew they were already paired up because we've already done the work on that, and then 1 left over here. Now, oftentimes I'll get questions from students about when do I know if it's up or down? It's a great question. In the way that we symbolically represent these electrons in these types of models, we always start with the electrons in the spin up configuration. It's actually one of those wacky features that you don't technically know what the spin is of your electrons, but you know that as soon as you put another one in there, it's going to do the opposite. So as soon as you have a pair, then they'll be counteracting each other. Anyway, it's kind of wacky. So in the way that we symbolically represent them, we always start with spin up. That's not something that you need to get too worked up over, depending on the level of chemistry that you're at. Okay, so here's different ways that we can represent physically the location of electrons on an atom. And this is important, again, because electrons have this wave-particle duality. So they have mass to them. We've talked about how tiny they are, kind of on the order of 10 to the negative 31 kilograms. So teeny tiny in terms of mass, but they also are energy, just like light. They have this potential to be both a packet of energy and have kind of a mass or a quantifiable amount of stuff associated with them. So that's what makes electrons a little bit wackier. Now, let's relate this to kind of how the heck would we even know how to set this up? And the answer to most of those types of questions of how would I know how to set this up is the periodic table, and that's what we're really building up to. But speaking of building up, there's a principle that we can use that's going to help to give us the order of the energy of each of our orbital types, and this is called the Aufbau principle. This is also called the building up principle. Which I like Aufbau better because it's just fun to say. And Aufbau will actually give you all of the different orbital types with respect to the current periodic table, the periodic table in its current form. This is kind of where we're at orbital wise. And here's how it looks. If you can draw this, then you will always know the order of your orbitals. So I start at the bottom, speaking of building up, and I start with the lowest energy orbital, which is my 1s. So I have an s orbital in the first shell, and that's all I have. So I gestured up to an atom that you couldn't see. In the first shell here, I have a 1s, and that's the only thing I have, and it can hold up to 2 electrons. Okay, now I can also have a 2s, I can have a 3s, I can have a 4s, and as I increase that principal quantum number, which is the big number out front, which tells me what shell I'm in, right? So this number, as it increases, we get further and further away from the nucleus, because as I increase my principal quantum number, I'm increasing in energy. So even though I have the same orbital type here, s's are the lowest energy level orbitals, they still have varying degrees of energy that are associated with them, and those varying degrees correspond to their size and the distance away from the nucleus. Okay. Now let's go to our p's. There are no p orbitals in the first shell, so we're going to start with the second shell, and we'll go up from there. And we'll find that 7 is a magic number, at least right now, 7 is a magic number for the periodic table, because, and again we'll relate this here in a second, the periodic table has 7 periods to it. So that's why we're going up here. We could go further than this. Could go above and beyond, but we're going to start here. All right, now if we go to d orbitals, the d orbitals start at the third shell. So we don't have any d orbitals in the first shell or in the second shell, but we do have them in the third shell. So we're going to go up from here. Oops, this should be a 4, 5, 6, 7. And then f orbitals, there are no f orbitals in the first, second, or third shell. They start in the fourth. So shall we? Okay, so with the Aufbau principle then, what we do to determine the lowest to highest energy is we build up. So we're going to start at the bottom and we're going to go up. So the 1s is the lowest. And then I'm going to go down to the bottom here and build up. So I went down and I said the next one's the 2s. Then I go down and I build up. I go to 2p, 3s, go back down, build up. This is why I'm not a mathematician, because I can't draw parallel lines. Then I go down to the bottom and draw up, down to the bottom and draw up, down to the bottom, draw up. Look at all my hard work that I'm just crossing out. Down to the bottom and up. Down to the bottom and up. And like I said, we could actually do this for F. We could do our G orbitals, H orbitals. We could go on from there depending on the level of chemistry that you're at. But let's just kind of start here as a principle. So if I was going to list out my order then based on this, I would say, well, it starts with my 1s, 2s, 2p, 3s, 3p, 4s, 3D, that's weird, 4P, 5S, 4D, 5P, 6S, okay, etc. So this is how I would read this thing. As I'm starting at the bottom, I'm working my way up and I'm following my arrows up, and then I'm going from lowest energy with my 1s here all the way up to my highest energy. So this kind of gives you a way to predict how to put these into the different, into the order, right? So it gives me my way of producing my boxes. And again, for S's, there's only one orientation for that. A sphere is a sphere is a sphere. For P's, you can have the X, Y, and Z axis. So there's 3 different orientations. For D's, there's 5. And for F's, there's 7. And so we're going to relate this then in the next video to how I can determine all of this information from the shape and the order on the periodic table. So keep an eye out for that one.